Okay, welcome students to video class number 27, uh, and we are on to the frequency domain analysis of the second order system, part 2. So we have in the previous video we have just seen what is the meaning of frequency response when you give a sinusoidal input. Okay, then you will be getting a response, or you can define that frequency response as a response when you give a sinusoidal input to it. And what's the speciality of giving a sinusoidal input to a linear system? When it is given to a linear system, the output will also be a sinusoidal of the same frequency, but they differ in magnitude and phase, and that results actually in the frequency response. So the frequency response is basically two types. They are magnitude response and phase response, and we have tried to plot the magnitude and phase response of a second order system. Okay, and we and you might be remembering in that class we have okay, I will be showing that again, that slide. Okay, we have defined some of the specifications like resonance frequency, peak resonance, cutoff frequency, and in this session we are going to find out some expressions or some equations for these frequency domain, for these parameters, and these parameters are called as the frequency domain specifications, and that too it is specifically for a second order system. And not only that, to be specific, it is for an underdamped system. What's the meaning of underdamped system? It's a system where theta is in between 0 and 1. Okay, now what do you mean by this resonant? So the first parameter that we are going, or the first specification that we are going to study, is the peak resonant frequency and peak resonance. And I have explained there what is this resonant frequency. Okay, so the peak resonance. Okay, you might be remembering. Okay, as shown, you have got a frequency response like this. And if you have any doubts, you may just refer the previous video. So this is how it is. Now you can see that the magnitude, when you plot the magnitude of the frequency response, that is m of omega. Now how to get the magnitude? Magnitude is, we will be getting the magnitude by putting s is equal to j omega to the magnitude of the transfer function. So you'll be using that when you vary different omega for this m of omega. We can find that this value starts from 1 and it goes up to a very high value, which is a peak value, and then after that point that reduces. So the maximum value, the peak resonance, this is referred as a peak resonance and is designated by the letter m suffix r, and it is given by the maximum value of the magnitude of the frequency response. Do you remember? It is the magnitude of the frequency response. So the maximum value is called as a peak response. Now coming into the resonant frequency, so this is actually related to, so the magnitude is depending on that frequency, so that will occur at a particular frequency. Obviously, as shown in this figure, you can see that at omega r, it is marked as omega r, at this frequency peak magnitude or peak resonance occurs, and that frequency at which the peak resonance occurs is called as a resonant frequency. Okay, now as I have mentioned that this is specifically to an underdamped system, means it is okay, where the damping ratio is in between 0 and 1. Now the question is, will there be a peak resonance for the whole range of 0 to 1? That's what we are going to, that we will be studying as we proceed our derivation. Now let's move on to the derivation. So first of all, we are going to find out the derivation for this resonant frequency and the peak resonance. So we will start with the that too of a second order system. We'll start with the m of s. You might be remembering the transfer function. So this is your transfer function. Okay, this is your transfer function. So this is your transfer function, which is given by omega n squared by s squared plus 2 theta omega ns plus omega n squared, and putting s is equal to j omega, you will get the frequency response. So that is s. So look at this, s is substituted as j omega over this equation, and you will be separating the imaginary and the real term. You will get that like this, 1 by and bringing this omega n square to the denominator, you will be getting, you can do it by yourself to arrive at this. We have already done this. Now this is of the form 1 by a plus jb. That means you can find out the magnitude of this 1. The numerator magnitude is 1. The denominator will be root of 1 minus omega by omega n the whole square plus 4 theta square omega square by omega n square. Okay, so hope you got it till this point. Now we have derived this equation. Now what we want to notice, we want to maximize this m of j omega, right? So how to maximize this? That is, our intention is to maximize this m of j omega. So what we need is, we need to find out this mr. So that means we want to find out the maximum value of this function. So this is a function. So when you look at this, you can see that the numerator remains 1. Well, it is the denominator which depends on the frequency. So you can have the condition in terms of frequency for the maximum value of this j omega by minimizing this value, right? Okay, this denominator. So let me call this as another q of omega, right? Okay, q of omega as root of, that is, I am just considering this denominator as a function of omega, calling this as q of omega as 1 by omega n the whole square plus 4 theta square omega by omega n the whole square, right? So this is it. Now how to proceed? Now that means this q of omega has to be minimum, right? It has to be minimum, right? I repeat again, for this m of j omega to be maximized, this I have assigned this denominator to be q of omega. This q of omega has to be minimum for m of j omega has to be maximum. So that means now in this q of omega, what I'm going to do is, I am assigning u to be equal to omega by omega n. Okay, I'm assigning another variable for this omega by omega n. So substituting that, you will get q of u. So I am calling this as omega. Since there is an omega, so I can call this as omega n is a constant. So it doesn't matter, you can call this as q of u is equal to root of 1 minus u square. That is putting omega by omega n as u plus 1 plus 4 theta square u square. Now the next point is, you can differentiate this dq of to du. Now when you differentiate this, okay, when you differentiate this, you will be getting this equation as 1 minus, you may do it by yourself, 1 minus u square into minus 2u plus 4 delta square into u divided by root of 1 minus u square the whole square plus 4, you have a whole square here, right? So this is root of the whole square. There is a whole square here, sorry. So that's it. So you will be getting this as 4 theta square u square, okay, which is equal to 0, right? That means you can equate this denominator to be equal to 0, or you will get u to be, on solving, you will be getting u to be 1 minus 2 theta square, okay, 1 minus 2 theta square. Now we can see that when you resubstitute this value, you will get this as omega by omega n is equal to root of 1 minus 2 theta square. Now what is this? This is actually the condition for, this is the condition, or I will write one more step. So this omega is equal to omega n into root of 1 minus 2 theta square is actually the condition for maximum resonance. Okay, this is the condition for maximum resonance. And now there is a problem for this. Now we know that this is actually your condition, and this is always a positive quantity because this is frequency. So the maximum value, so it has to be always positive. That means 1 minus 2 zeta square has to be positive. It cannot be imaginary as well. Now let us see at what point this omega becomes equal to 0. That means this has to be valid only for a certain value, right? So now we know that as theta increases, this particular value increases, right? And a stage will be coming where this quantity becomes a negative value. Now once it becomes a negative value, this becomes imaginary. That means omega cannot be an imaginary quantity. Even though omega is plotted in the imaginary axis, omega as such is not an imaginary quantity. That means it cannot be. So we need to find out at what point of theta this whole value becomes equal to 0. That's it, right? Once theta gets increased, this 1 minus 2 theta is going to say, look at this, as theta increases, what happens to 1 minus 2 theta square? That decreases, right? And it will go beyond a point 0. Once if it goes beyond a point 0, this becomes an imaginary quantity because this becomes root of minus a quantity. So that should not be allowed. So in that context, when you equate this 1 minus 2 theta square to 0, you will get the value to be, the theta value to be 0.707. You can just look at your calculator, say just substitute 0.707. This almost becomes equal to 0. 1 minus, it will be 0.9999. This will almost becomes equal to 0. So that means this is actually the condition for maximum resonance, and this maximum resonance is related to what? Related to the damping ratio in such a way that maximum resonance occurs only for the value between theta for between 0 and 0.707. Okay, that's the point. So you need to be very careful in this. So hope you understood this. So what you did is you just assumed u to be omega by omega and done the derivation and obtained the condition, and again replace that u by omega, and so this is actually the frequency at which this this is the condition for the maximum resonance, and from this condition we have derived another condition in terms of damping ratio that if it requires a real frequency, then theta has to be between 0 to 0.701. Even though, say, for an underdamped condition, theta varies from 0 to 1. Because of this problem, the theta gets restricted to 0.707. That is to what? That is for this maximum resonance. Okay, so that means you can have a scenario like this as well. Say, without going to, so a magnitude response can be in this way. That means in this case you don't have a maximum resonance, no maximum resonance. And what must be the reason? That means if it is theta, this is for the value theta greater than 0.707. This is for the value between 0 theta less than 0.707. Hope you understood this. Okay. So now we have seen that this omega is the frequency at which the maximum resonance occurs, and that is what is called as the resonance frequency. So resonance frequency is omega r is equal to omega n, which is the natural frequency, 1 minus 2 theta square. Do remember maximum, this is the equation for maximum resonance, okay, or for the peak resonance, and this is valid only for theta less than 0.707. This is very, very important, this observation. Okay, now how to find out the peak resonance? Now it is very simple. Now the peak resonance can be obtained by substituting this condition to this magnitude m of j omega, and you will get that as, okay, so you will be getting like this. So what I did is just substitute omega as omega n into root of 1 minus 2 theta square. So you may just do it by yourself, and you should get this equation. Mr is equal to, the peak resonance is equal to 1 minus 2 delta theta divided by root of 1 minus theta square. And this condition is very important because this is the condition we got from the resonance frequency. For the resonance frequency to exist or in a real point, theta has to be this. That means maximum resonance occurs only for these values in between 0 and that's what I have explained with this caret. Okay, so no peak resonance will be there. Okay, right. Now next is the cutoff frequency. What do you mean by cutoff frequency? It is defined as the frequency at which the magnitude of the response becomes 0.70 of 071 of the initial value, as I've already explained in the previous video. That look at this is the magnitude response of a second order system, and we have this is 1. That's that is a value at t is equal to omega is equal to 0. Now this at a particular omega, we can see that the value is going to be 0.707 of the initial value. The initial value was 1 and it is just the 70% of this. Now this is actually the point corresponding to half power points, and it is at the half power points we usually define this cutoff frequency, as you might have studied in your filter design classes. Okay, so this 0.707 is an important value as far as the filter design is concerned. So there you will define this cutoff frequency. Okay, now this is the frequency at which this becomes is called as a cutoff frequency, and it is designated by the letter omega c. Now how to find out this omega c? Now to find the I will just explain. So this is the magnitude, right? Now this magnitude must be equal to 0.707 of the initial value. What was the initial value? The initial value was 1. So that means 0.701 of the initial value is equal to 0.701, and equating that you will get this as. Okay, now substituting this, so you can use that magnitude equation. Using that magnitude equation, it is equated to 0.707, and now I am just for the simplification, I am just assigning a variable x to be omega c by omega n, so that you will get this equation in this way, right? So that is, you can rewrite this expression as root of 1 minus x the whole square, x square, 1 minus x square the whole square, plus 4 delta square x square, okay, it is equal to 1 by 0.707. okay, right, from this equation you can write like this. Now squaring this, you will get this as 1 minus x square the whole square plus 4 delta square x square is equal to 1 by 0.707 square. Now when you do that calculation, you can see that this is equal to 2, right? Now that means you will be having, now when you simplify this, you will be getting like this: x raised to 4 minus 2 into 1 minus 2 zeta square, 1 minus 2 zeta square into x square minus 1 is equal to 2. So you may just verify. So just expanding this, and you will be arriving at this expression. Okay, now solving this equation, okay, so solving this equation, you will get this as, how to solve this? So say assign another variable for to be, say x square as p, put x square as p, so that this becomes a quadratic equation. So you'll be getting a equation. So x square, so and use apply minus b plus or minus root of b square minus 4ac. So I'm not going to do that for you anyway. So you will be getting this x square to be, if you want you may do that by yourself. Okay, so plus root of 1 minus 2 theta square the whole square plus 1. Okay, so what will be x? X will be root of 1 minus 2 theta square plus root of 1 minus 2 theta square the whole square inside this root. Okay, plus 1, right? Okay, you can expand this, and expanding this. Now what is this x? X is defined to be omega c by omega n. So substituting that, omega c by omega n is equal to root of 1 minus 2 zeta square plus root of, you can expand this and you will be getting this as the final equation will be 4 delta square plus, right, 4 delta square plus 4, this is minus, plus 4 delta raised to 4, right? Okay, so you'll be getting an expression like this. So what is your cutoff frequency? Cutoff frequency is omega n into root of 1 minus 2 zeta square plus root of 2 minus 4 delta square plus 4 delta raised to, zeta. It's not delta. I'm sorry, I think I have used that term. Do remember, it's just correct. It is zeta. Okay. So this is zeta raised to 4. Okay. So when you plot omega c by omega n, where's the theta here, right? That is omega c by omega n. Where's the theta? What happens at value 0? So otherwise you may just look at this. So the value at theta equal to 0, this quantity becomes 0. That means this is root 2 plus again 1, root of 1 plus root 2. Okay, so you can see that at theta is equal to 0, this comes around, this omega c by omega n becomes equal to 1.55 at theta equal to 0. Now what happens at theta equal to 0.707? At 0.707, omega c becomes omega c n by omega n is equal to 1, or it is the point where omega c becomes equal to the natural frequency. Now beyond that, if it goes, it will be oscillating. So omega c is equal to natural frequency means that is the sustained oscillation. It will be like this, right? So this is the condition for theta. Now once this is the condition where omega c is equal to omega n, and that's where theta becomes equal to 0.707. So you can plot this graph as like this. This will be starting from 1.55, okay, and it will be moving in this way. So this is omega by omega n will be 1 at 0.707. So that means now this is actually the now this omega c is actually the cutoff frequency. Now you can see that the bandwidth will be equal to bandwidth will be equal to omega c itself. Okay, so that is it. So that means you can come to a conclusion that as theta increases, what happens to the bandwidth? The bandwidth decreases, right? That's what this shows. So as theta increases, this bandwidth is going to decrease. That is the conclusion that we can draw out from this. Okay.